solving a right triangle refers to finding the lengths of all the sides and the size of all of the angles. So that if we want to solve the triangle in which one of the angles is 65 degrees 12 minutes and side A is 14.2, then it means that we want to find the other angles and the lengths of the other sides. Well, there's a particular notation that goes along with this idea as well. Now notice a lowercase a and an uppercase b here, and it turns out that the notation looks like this. That generally the uppercase letters refer to angles and the lowercase letter refer to the lengths of sides. And in right triangles we generally write the angle C right here as the right angle, and side C, lowercase c, would be opposite that, that angle. Now I'm setting it up with C here because it'll correspond with the c squared is a squared plus b squared idea that we use with the Pythagorean relationship. Now either of these other two angles could be A and the other then would be B, but if this one is uppercase A, this one would be uppercase B. And this then, the side opposite this angle B would be lowercase b, and the side opposite uppercase A would be lowercase a. So that's how we set up the notation. Now if side A is 14.2, that means this side is 14.2. And if angle B is 65 degrees 12 minutes, that means this is the angle that is 65 degrees 12 minutes. Okay. We want to solve the triangle, and that means finding the lengths of sides and sizes of angles. And gee, the size of the angle here would be pretty simple, wouldn't it? Because all we have to do is realize that there are 180 degrees total in a triangle. We have 90 degrees taken up right here. So these two together total 90 degrees. So all we have to do is take 90 degrees and subtract the 65 degrees 12 minutes. Well, when minutes are involved like this, there's a little trick involved with the arithmetic, and it works like this. Now, angle A is found by taking 90 degrees and subtracting 65 degrees 12 minutes. But in order to accomplish this subtraction, we actually end up borrowing from the 90 degrees. We think about this as 89 degrees plus one other degree, and that one other degree is really 60 minutes. So we think about it like this. It's 89 degrees, 60 minutes, and we're going to subtract 65 degrees 12 minutes to get 24 degrees 48 minutes. So A is 24 degrees 48 minutes, and we transfer our information back to the problem. And we would probably put that information right here. And I'm getting a little jammed. Okay, now we'd like to find the lengths of the other two sides. Now, generally speaking, in problems like this, when you are solving a triangle, I would suggest that as often as possible, you use given information in order to make the calculation on something that you don't know. Now, by that I mean this, that if we are thinking about solving or finding the value b, then we might think, well, from the perspective of this angle, we can think about b and the 14.2 related to one another by the idea of tangent or something like that. And certainly we could do that. So we could use the tangent of the tangent of angle A is 14.2 over b, and that would probably be just fine. But the safer thing to do is to use the given information about angle B and involve this given side and also side B. Now we're still using tangent here, but it's the idea of using the information about the given angle rather than the one that we calculated, because occasionally you'll make a mistake in these problems, and if we have a small mistake here, then the calculation of B will have a mistake in it as well. Okay, so just as kind of a safety net situation. All right, so from the perspective of the given angle, we're thinking about the given side and also a side that we want information about. And so it's opposite side over adjacent, and that's the tangent function. So the tangent of 65 degrees 12 minutes is b over 14.2. So we come over here and make a calculation. The tangent of 65 degrees 12 minutes is b over 14.2. To multiply on both sides by 14.2, and we find b to be 14.2 times tangent 65 degrees 12 minutes. Now be careful in entering this into the calculator. That's what the great challenge is here, I think, that we have to make sure that we understand that 12 minutes is 12/60ths of a degree. So we have to enter 12 divided by 60 and then add 65, you see, for the total number of degrees in the angle. All right, and then the tangent of that amount and then multiply times 14.2, and we find B to be approximately 30.7 degrees. So 30.7, excuse me. We're finding a side here, so it's not degrees. It's 30.7 is the length of this side. Okay, now for side C, you see, now once again, I want to caution you about using information that you have calculated. And by the way, this is, I should write approximately equal to here, because this is a long-winded decimal that we rounded to this point. And if I used this value in the calculation of C, then I'm using a mistake. It's a small mistake maybe, but a mistake nonetheless, and we don't want to create an additional mistake for the value of C. So what we want to do in calculating C is involve the given angle, the given side, and side C. Now think about a relationship that involves this and that, and this angle. From the perspective of this angle, we're talking about adjacent side and hypotenuse, so that's the cosine idea. So we would come over to the side and write cosine 65 degrees, 12 minutes equals 14.2 over C. Now, again, I want to talk to you about structure here in the calculation of the problem. Notice that C, the unknown quantity, is in a denominator here. And because it's in a denominator, we would have to multiply on both sides by C to clear the fraction, and then we would end up dividing on both sides by this. So it's a little bit of a manipulative process. Now, we might have elected to save ourselves a little bit of time, maybe, by using the reciprocal function here so that we would get the unknown quantity in the numerator over here. Now, we don't have to do that, but I just want to tell you that it's an option, and it's an option you may wish to exercise from time to time. So we might think about secant, then, of the angle being the hypotenuse over the adjacent side, so that would be C over the adjacent side, 14.2. You see, and then using this technique, C then is 14.2 times secant 65 degrees, 12 minutes. And then you punch your calculator to get this. Now, to punch the calculator for this, let's assume that we have the value for the correct number of degrees for this in a decimal form. Then what we find is, on the calculator only has sine, cosine, and tangent. So we would find the cosine of that, and then it's reciprocal, you see, for secant. And then, once we have that reciprocal, we multiply by 14.2. We find C to be approximately 33.9. And at this point, we have solved the entire triangle. Now, make sure you have identified every angle and every side before you decide that you're finished with these problems. Because sometimes after you've accomplished one of those items, you kind of think that you're all done. But just be careful. Consider this problem. At a point 200 feet from the base of a building, the angle of elevation to the bottom of a smokestack is 35 degrees, whereas the angle of elevation to the top is 53 degrees. Find the height S of the smokestack alone. In problems like this, it's often helpful to draw a diagram. It'll help us to understand the problem, and it'll help us understand the nature of our solution. Here's a diagram of this problem. Now, here's the building, here's the smokestack. Now, notice 200 feet away, the angle of elevation to the top of the building is 35 degrees. The angle of elevation to the top of the smokestack is 53 degrees. All right, I've labeled the height of the building as A, and the smokestack itself is S. Now, we might look at the problem, and by the way, this would be a good time to copy the problem and try the problem on your own and then come back and roll the tape, because you end up pondering these diagrams a little bit to decide what we're going to do next. And when you go through that pondering process, you understand that, gee, we have a right triangle situation here. And in right triangle situations, we have our three trig ratios available. We're going to use the information about this lower side You see, and we're going to use these angles involved. And the side opposite those angles are these sides. You see, and we have the smaller triangle that has to do with the height of the building, and we have the larger triangle that has to do with the height of both the building and the smokestack. So what we're going to end up doing is finding the height of both the building with the smokestack, and then we'll find the height of the building, and then we'll take the difference between the two. It doesn't matter which one we find first, whether it's the building or the building and the smokestack, but at any rate, we're just going to find the difference of the two. Okay, so let's do that. If we are talking about finding the height of the building first, then we're dealing with this little right triangle, and the angle here is 35 degrees. So we're talking about a 35-degree angle here, and we're talking about, from that perspective, opposite side over adjacent side. Aha, tangent. So it's the tangent, then, of the 35-degree angle is equal to the opposite side, A, over 200. Multiplying by 200 on both sides, we can calculate A as 200 tangent 35 degrees. And using the calculator, we find A to be approximately 140 feet. All right, now for the building with the smokestack, we reason this way. Now once again, it's the opposite side and the adjacent side that we're dealing with, so that's the tangent notion, or cotangent. But I'm using tangent here if for no other reason than the idea that I'm going to have the unknown quantity in the numerator of my fraction. So I've got tangent then of 53 degrees is, now this total distance on the opposite side is really A plus S. It's the sum of these two. So it's A plus S over the 200 feet. And now the distance A plus S is equal to 200 times tangent 53. And approximating this, we find that total height to be approximately, and I should use approximation here, 265 feet. Now the idea is to take the difference between these two. Now the difference between these two, as you can see, is approximately, I think it's 125 feet. 125 feet approximately is the height of the smokestack. Now if I were doing this though, on my own, I would probably set it up or make the calculation using the calculator a little bit differently, because I would want to use, instead of these two separate approximations, subtracting two approximations could cause us to have an error that would be greater than we would have if we used exact values. You see, what I would want to do is take this 200 tangent 53 degrees and subtract 200 tangent 35 degrees, because that's an exact value for the building and the smokestack together, and this is an exact value for the building alone. In other words, I would probably do it like this. I would think, okay, the smokestack is equal to the smokestack plus the building, and the smokestack height is the smokestack plus the building minus the height of the building, and the smokestack plus the building is 200 tangent 53 degrees. And the building by itself is 200 tangent 35 degrees. So I would use this in the calculator, and I would still find the value to be 125 feet for the approximate height of the smokestack. So it may not make a big difference in this problem, but it could in other problems, and especially in problems that might involve some very critical kinds of calculations. Suppose an airplane is taking off at a rate of 275 feet per second on some unknown angle of ascent, and after 1 minute the plane is 8,773 feet high. We'd like to know the angle of ascent. Now this problem is a little different than the other problems that we've seen, because we're not trying to find one of the sides of a triangle, we're actually trying to find the angle involved in a right triangle. Well, just from the idea of a right triangle and finding an angle given the length of that opposite side and some information about this side, we kind of have a hint that we're going to be talking about the opposite side over the hypotenuse. Oh, that's the idea of sine. However, we don't have the length of this side. We have a speed associated with the length of this side, though. That jet is traveling at this rate of speed for 1 minute to give us the length of this side. So let's make the calculation for that distance. Now we know that distance is rate times time. And the distance then is a rate of 275 feet per second times 1 minute, which is a time of 60 seconds. Now I'm putting the units here for emphasis because when we use the units within calculations like this, a lot of times we can make the calculation of the unit that results from the calculation by just looking at the cancellation opportunities. Here we have the seconds are canceling here, you see, and so our answer is going to be in feet. So we have 275 times 60, and that distance then turns out to be 16,500 feet. So along this side then, we have 16,500 feet, and now we can make the calculation for theta. Now from this perspective, it's the sine because it's opposite over hypotenuse. So sine theta then is opposite over hypotenuse. And now we want theta. We want theta. We want the angle whose sine is this fraction. Well, that's arc sine or inverse sine, you see. And from a strictly algebraic standpoint, we can think, well, sine is just some kind of operation, and so if we just undo that operation on both sides, we'll isolate the theta. And undo sine is the same as inverse sine. So we inverse sine here, inverse sine there, and we isolate theta. Just another way to look at it. But mathematically, it's best to think, well, this is a request for an angle whose sine is this amount. And to make the request trigonometrically, theta is arc sine of that fraction. Using the calculator, now we use the calculator by inverse sine, you know, second function on sine, and then enter the fraction, press enter, we find theta to be approximately 28 degrees. An airplane flying at 550 miles per hour has a bearing of north 52 degrees east. After flying for 1.5 hours, how far north and how far east has the plane traveled from its point of departure? Here's the important information given in the problem. The rate of speed is 550 miles per hour. The bearing is north 52 degrees east, and we'll talk about that in a second. And the travel time is 1.5 hours. Now, this bearing, this notation for bearing means this. It means that if this is the northerly direction, and of course that would be south, but it's like let's consider the northerly direction and then consider an angle of 52 degrees toward the east from this north. You see, and that's the idea. It is from north, measure 52 degrees toward the east. Now, let's see, which would be the east? If this is north, that's west, and that's east. Okay, so toward the east, we're talking about a 52 degree angle. Let's say that that's 52 degrees. Now, we're trying to find, let me stay with this bearing idea just for a moment. There are actually a couple of ways to describe direction using navigation. And one of them is using this idea of some angle off of a north-south line. Another bearing might be something like this. How about south 20 degrees west? What does that mean? It means if we're heading south and we measure an angle that is 20 degrees toward the west, well, from south, which is west and east? Well, that would be west, that would be east, and so 20 degrees toward the west would be the direction that we're talking about. If that's 20 degrees, then this is the direction that we're discussing. Okay. Another way to describe bearing is in terms of a single angle measured clockwise from north. That is, if it said we were on a bearing of 200 degrees, then it would be 200 degrees measured from due north. It would be kind of like this. It would be, here's north. Now let's measure an angle. We're talking about, here's our point, but let's consider an angle of 200 degrees. There's 180, there's about 200. Okay, so we're going in this direction, you see. All right, clockwise from north. Another way to do it. Now, in this problem, we'd like to know how far east and how far north the airplane has traveled from this initial point. Now, the airplane is traveling for 1.5 hours in that direction at a speed of 550 miles per hour. But how far has the airplane gone? We need a distance here. If we're going to calculate the distances for the northerly travel and the easterly travel, you see, and that's what we're doing. We're setting up a right triangle configuration here, and we'd like to know this northerly distance, and let's call it little n, and the easterly distance traveled by the plane. Then we need a value here for this hypotenuse, and that value should be in miles. Oh, well, we can easily do that. We know distance is rate times time. We have a rate of 550 miles per hour and a time of 1.5 hours. So we come out here and we say distance is rate times time. The rate is 550. The time is 1.5 hours. Now, once again, notice I've used the units here just to illustrate the idea of the possibility of seeing the cancellation of hours, and that our resulting unit of measure needs to be miles here. So, and it's not really a surprise in this problem, but it might be an important matter in future problems. Okay, our distance here then is 825 miles. All right, now we start to calculate the n and the e involved in this right triangle. Okay, we're talking about an angle here of 52 degrees, so this is our the perspective from which we're thinking about ratios. And if we're going to calculate n, the northerly distance, you see, then from the perspective of this angle, we're talking about the adjacent side and the hypotenuse. So let's see, that adjacent side hypotenuse, that's cosine. So the cosine of 52 degrees is n over 825. So we come out over here, cosine of 52 degrees is n over 825. Multiplying by 825 on both sides, we'll calculate the value of n. It'll be 825 times cosine 52 degrees. And when we use the calculator, we find this amount to be approximately, and I'm looking over here because I have it written on the bottom of the board, 508 miles. Now, so this then is about 508 miles. Now, when we now arrive at the point of calculating E, are we going to use, you see, from the perspective of this angle, are we going to use the 508 with the E, or are we going to use the 825 with the E? Well, we're certainly not going to use the 508 because it's an approximation. You see, we want to use the given information and what we're looking for as well. So we use 52 degrees, the 825, and the E. Now, from the perspective of this angle, we're talking about opposite side and hypotenuse. That's the sine idea. So the sine then of 52 degrees is equal to E over 825. E then is 825 sine 52 degrees. And with the calculator, we find E to be approximately 650 miles. So the airplane has gone, after this 1.5 hours at 550 miles per hour on a bearing of north 52 degrees east, the airplane has traveled north 508 miles and east 650 miles approximately.